Hi everyone, my name is Gabriel Salim. I'm part of Group 16, and I'll be taking you through the first slides of our project entitled Large Acoustic Models for Video Generation with Large Vision Embedding. Just explain the key terms. Large acoustic models, these are deep neural networks that are trained on a large data set of audio data for audio interpretation. And then visual generation means interpreting what's taking place in a scene, depending on the context and dynamics that are in the scene. To begin with, according to World Health Organization, globally, there are 2.2 billion people that have vision impairments. And out of these 2.2 billion people, 43 million is totally blind. What does this mean? It means that for these 43 million, understanding what's taking place in a scene is not only an inconvenience, but it's a challenge that they have to deal with in every second of their lives. And we know humans understand what's taking place in the scenes, depending on the narration and then the perception. But then, for example, let's say a certain individual enters a room, what they have to do is they form a semantic understanding of the objects in the room, how safe it is and how urgent it is. But then we've seen that in assistive technology, this idea is the development of audio-based systems translating sensory information into spoken feedback. And in recent advances in multimodal AI, it has made it possible to convert these visual scenes into text and then into speech. They have also gone ahead to promise the blind people to give them visual information through audio. However, the existing acoustic system doing narration as just a secondary output. They focus on object detection, best skin labeling, and contextual narration. This is a problem because most acoustic systems don't focus on how scenes are actually narrated to the blind. And focusing on our main computation problem of generating how human-like emotion-aware audio in real time while interpreting dynamic scenes, are explaining emotions and also expressivity like humans. These acoustic systems that are currently there, they lack semantic narration, whereby, for example, instead of explaining what's actually taking place in a scene, they go on to only describe the objects. For example, let's say there are cars moving and there are people. They just say there are cars, there are people, and red lights. That's only what they will say. But then in semantic understanding, you have to say there are people moving. You're in a busy environment with a lot of movements. Cars have stopped, which shows that your movements have to be cautious. That's semantic narration. And then they produce speech that is emotionally flat and unexpressive, whereby these existing acoustic systems, they are emotionally flat, they sound robotic, and they are monotone. They don't express themselves as humans, and then they don't have that element of story-like narration. And to address this, we are going to develop an acoustic system that goes beyond this contextual narration, and instead it provides semantic and emotionally expressive narration for the blind users. These are the recent works that we made research about. For example, there's a work about smart eye vision, which integrates a camera, a Raspberry Pi as the processor, and then the mobile net as the object detector, and then the text-to-speech module. But then the limitation is the audio the audio feedback that is generated is basic, and it lacks emotional modulation. Same applies to the other papers that we reviewed and other systems. For example, the voice assistant for the blind, which also integrates a camera, a CNN for object detection, then a text-to-speech module, and then audio. But the audio that is given out, the feedback is limited to short, discrete announcements and lacks contextual interpretations of the scenes. And then the last one, if I'm to sample the last one for the audio side, which is enabling ambient interaction for blind and visually impaired individuals. It also integrates multimodal sensing, contextual inference, and speech output. But the problem is the auditory feedback is event-driven, and it also lacks expressiveness and also continuous narration. Thank you very much.
Hello, sir. And by the name is Munaka Chikajavia, and I'm going to take you through the research questions and the objectives. So the research questions are derived from the research gaps that we were able to identify from our related works. And some of these are the current systems lack expressive speech, and when they are narrating the scene, they are monotonic. They sound like robots. They don't dive deep into the real meaning of the scene. So the questions that we asked ourselves, that we came up with from these related works include: how can the semantic scene understanding be integrated to guide emotion and expressivity of the narration? How can the system generate contextually accurate and meaningful narration of real-world scenes for blind users? We want to create a system that is contextually accurate and that gives emotion when narrating these real-world scenes to the users. Then how can the multimodal architecture be optimized to deliver seamless real-time storytelling without losing the semantic richness? We want to give blind users the real-time storytelling without losing the real understanding or the real meaning of what is happening in the scene. Then some of the research objectives include to develop a system that produces contextually accurate and meaningful narration to the real world scenes for blind users. The objectives answer the questions, and also to fine-tune the language generation model and LAM into turning narration into an engaging auditory story rather than a monotone feedback, like I said, one of the research gaps that we found. Then to optimize model reference and fusion strategies so the narration remains coherent, responsive, and contextually adaptive. Then the research contributions, we want to develop a system that enables system understanding based narration for blind users by integrating their the perception which it received from the scene, semantic understanding, and acoustic generation. We want to be able to deliver this real-time storytelling, but with the semantic understanding of the scene. Then also we want to develop a system that produces natural, expressive, and human-like auditory feedback that is not monotonic, improving the quality and clarity of the outputs. Then we want to build a system that changes dynamically with a changing environment or the changing scene. Thank you. I'll invite the next speaker.
My name is Naomi Mnezero, and I'm going to take you through dataset description and exploratory data analysis. So we chose two datasets that are publicly available, and the first one is Ego 4D, that is from Shared GPT videos on Hugging Face. So this is for vision to text fine-tuning, and therefore it contains video text pairs. So we have 70 video clips, and we have a JSON file that is containing 70 captions from those 70 videos and corresponding path to the videos. And we performed EDA on this dataset, where we got this histogram that is showing duration distribution. And it showed us that most of the videos have durations that lie between 56 to 60 seconds, which is showing us that we do not have many videos that are too short or too long. And the second visualization is a word cloud that is showing us the frequency of certain vocabularies in the captions, where we have words like hands, within, and others appearing most. And this shows us that the dataset is actually showing real-life narrations. So the third visualization on the Ego 4D dataset is a box plot that is showing word count, where we have most of the captions having words lying between 260 to 350 words. Yeah, which is a balance because we do not have videos that have very few words or very many words. The second dataset is called Emotional Voices dataset, and its source is Open Speech and Language Resources. So this dataset is for fine-tuning the acoustic model. Therefore, it contains audio text pairs or audios and their transcriptions, where we have 4 speakers, 2 males and 2 females. And each speaker is having 5 emotional categories, where we have amused, angry, disgusted, sleepy, and neutral. So the first visualization on this dataset is a heat map that is showing speakers versus emotions, where we're having almost all the speakers having audios for all the emotions, except Josh, who is lacking the audios on the emotions of angry and disgusted. The second visualization on this Emotional Voices dataset is a histogram that is showing total samples per emotions, where we have emotions like sleepy having more samples compared to emotions like disgusted that is having a few samples. And then the final visualization on Emotional Voices dataset is also a box plot that is showing audio durations by emotional categories, and we are having some emotional categories like sleepy, disgusted having bigger durations compared to emotions like angry that are having shorter durations.
Well, my name is Kasha Alvin Sadi. I'm a member of Group 16, and I'll be taking you through the methodology for our project called Large Acoustic Models for Visual Simulation of Large Visual Embeddings. So the proposed methodology starts off with an input video. That this input video is from, of course, a wearable camera, and it is passed into a large vision model that the large vision model, you could think of it as a deep neural network that is trained on massive image data sets, and it's used for tasks of image understanding and video understanding in the modern technology. So this large vision model generates large visual embeddings. Now the large visual embeddings are the cinematic representations of what's actually captured in the input video. Let it be objects and also contextual relationships between the objects, and it passes them to a projection layer. Now the use of this projection layer is simply to align these large visual embeddings into visual tokens that are expected as input to the language generation model. Now this language generation model will be fine-tuned on the video text data set, provide a detailed description of what is actually happening in the scene. So after generating this scene narration text, it passes it into the large acoustic model that will be fine-tuned for expressive speech. So this large acoustic model provides the auditory feedback that has the narration based on scene understanding, describing what's actually happening in the scene. Then after that, this auditory feedback will also have the tone of expressive speech. So these will be delivered back to the blind person through the earbuds. So that will be the auditory feedback. Then next, we've been doing some work and we've managed to fine-tune one of these models, and this model is called the LavaNext Video, which is a multi-model having a large vision model, this vision encoder being the CLIP VIT large vision transformer large, and then the language backbone being the Luna 7B large language model. So we fine-tuned the LLM part of this multi-model using LoRa or low rank adaptation that helps us like fine-tune the trainable parameters of the LLM part of this model. So we fine-tuned it for 3 epochs, and for each epoch there were 17 iterations. So the total was 51 iterations for the 3 epoch. So you could see the training loss with this dim blue line. So it was decreasing over the number of iterations over the number of epochs. And you could also, the validation loss was also decreasing over the number of, as the epoch number went on increasing. So you could see that the narrow margin between the training loss and the validation loss simply meant that the model was actually generalizing well on the scene data. And the scene data was also part of the validation set. So it means this model was not actually relying on memorizing the training samples, but also working with describing data that is unseen or data that was not part of the training set. So this, after fine-tuning, of course, we had to compare between the old model and also the fine-tuned model. So you could see that the old model response was a text, but not so descriptive. It was only 5 sentences. But then the new model response, after using low rank adaptation, parameter efficient fine-tuning on the LLM part of the model was able to generate a descriptive text describing what's actually happening in the scene, capturing objects, contextual relations between objects, the sequence of actions, and also the element of scene understanding. Then we went on to design a user interface for accessing the model. So we could upload a video here, and then the model could provide a detailed narration based on scene understanding, describing what's happening in the scene. So you could see it was able to describe the objects in the scene, keyboard, mouse. Then the scene element perspective was the state of concentration by the individual, the user. And then this also suggested a busy workspace. So you could see the model was able to go beyond and understand the video and explain what's actually happening in the video. Then this work, of course, demonstrates that integrating scene understanding with specific auditory narration can move assistive systems beyond simple auditory feedback. So the auditory feedback provided to the blind user should not only describe things that are in a scene, but should go on beyond to describe why things are happening in the scene. That's what I've been demonstrating to you. As I guess the person is in a state of concentration and it's a busy workspace. So this will help the blind individuals improve their environmental awareness and user experience. Thank you very much.